Well, hello. We're starting our December structural modeling video conference, and today we're going to be talking about structural modeling software, the basic components for that that we developed over the last couple of years. And this is going to be kind of a transition from we're going through now from just talking about a lot of the mathematics and fundamental aspects of the structural modeling processes and methods, and now start segregating those out and starting matching those directly to software components. So the paper's been out there for a few days. Is there anything in the report people would like to have emphasized, or should we just start at the top and walk through it?
I'd like to understand better why the math for doing what you're calling multi-thread or partial orders is another level to attain.
Okay, that's really that's a good point, Kevin. And I guess one of the things to start thinking about in that case is to think about different relationships. And if you think about a relationship that creates a sequence, right? Heavier than, bigger than, north of, south of, east of, west of, those all create a sequential type of relationship. And those then tend to generate a single-threaded type of relationship structure. Then we have other relationships that are not single-threaded. They're multi-threaded, and those multi-threaded relationships, then basically you can think of it when you're thinking about it in the matrix form, to kind of leave gaps, or it leaves zeros in the lower triangular part, because there's not a pathway through that connects everything, right? It's a reachability matrix, and if things are not reachable, right, which in multi-threaded cases usually is the case, there's stuff that's not reachable by every component, because if it is reachable by every component, then usually it'll be single-threaded. So that's kind of the idea. The idea is that the lower triangular piece, if you're thinking about it in the mathematical matrix form, instead of being all filled with ones, which is single-threaded, it has zeros in it. And so you cannot rely on that lower triangular piece for inference. So that's kind of the basic for that, and I'll kind of emphasize that as I walk through this. Anything else?
Yeah, I think yes, I agree with Kevin. It would be good to, and what you're saying there, it would be good to walk through the whole report for the sake, in part, of the coherence of the tape, and then emphasize this topic as you go.
Okay, well then we'll just do that. So in the introduction, what we're doing now is we're talking about the structural modeling software that was developed to support structural modeling activities. And of course, you need the structural modeling software to assist in the inference piece. And the inference piece in structural modeling is one of the points where you leverage and greatly reduce resources, because you don't have to go get every piece of information. So you could go get every piece of information. That'd be very expensive if you had the time and resources to do it. In many cases, people in very large-scale systems don't even have, wouldn't even have the time to go through and get all of the permutations and get all of the information. Use inference if the relationship is correct and if the semantics of the situation is correct. So we use that to help reduce the resources and also reduce the logical errors. And so it's been pointed out before by some authors that you can do these operations by hand on smaller situations. That would be, that's true, you can do it, but there's also the problem of human error becoming involved in every activity. And then if you encode the algorithms into software, then there's also the problem of encoding mistakes or errors in the software or improperly applying the algorithm semantically in the wrong space. So those are kind of some of the challenges that we're trying to address with open source software, because with open source software, you can look at the software, you can understand the processes, you can understand that the semantics agree with the place that you're going to apply them, and allows a number of people to look at the software, to understand it, and to improve it or make corrections or additions to it if they feel it's necessary. So that's basically what we're doing as we start going through the software analysis. And so the first thing that we did was to expand the 3 basic systems types, expanded it to 5 types. And the 5 types are there's 2 asymmetric types in the hierarchy and 2 non-symmetric types. And then, of course, the symmetric network type. So just emphasize the fact that we have the single-threaded hierarchy and a single-threaded non-symmetric combined hierarchy and network. And the single-threaded network should generate a matrix representation that has all ones in the lower triangular. Whereas on the multi-threaded one, if you do the mapping on this, then essentially there's going to be some of the lower triangular ones that are not reachable from other points. And so like the two in the multi-threaded one, the asymmetric, their hierarchy right here in the right here in this area. That's, oh, wait a minute. That's on right here in this area. Come on. I don't see it on the screen either, but it's on the multi-threaded area. Okay, not coming through. My pointer's not coming through on the screen. So in the multi-threaded one, in the second tier down, we have 2 objects side by side. They're not reachable from each other. So there would be some zeros involved there. Then in the combined hierarchy and network, this is a fairly basic idea of taking a network and condensing it into an element so that the single thread in the non-symmetric piece essentially winds up looking like a single thread in the hierarchy. Similarly, the multi-thread, once the clusters are condensed, wind up looking like a multi-thread in the hierarchy. And then, of course, there's the symmetric piece, or the clustering piece. And there's a key semantic idea that relates to clustering. What is it? What does it mean? How do you evaluate it and condense these objects or these clusters into a single object? What's the process for doing that? Does the semantics change during that process? So we're going to, in our next reports, we're going to start focusing on the network clustering piece, what these different definitions that we've located in the literature, and then how we're going to address it and the software. So essentially, we'll be moving a little bit more away from the hierarchy piece and focusing on the clustering network piece in the next couple of technical reports. So what we found is that even though the logical property groups are important in looking at and evaluating in the semantics of structure, they're really not a key discriminator. Because as you can see here in the single-threaded one, this is a irreflexive, asymmetric, transitive relationship that creates a single thread. In the multi-threaded one, in the hierarchy, you can see it's irreflexive, asymmetric, and transitive. And so they both have the same logical properties, but they appear to need different algorithms. So there is another concept, another idea, there's another set of semantics appear to be needed to properly identify and discriminate between the algorithms, and that has to be different than appears to be different than the logical sets. And what we started out with is calling them the global attribute and the local attribute. And these are some ideas and name tags we give to the fact that a global single-threaded relationship applies globally, and a local multi-threaded or variable-threaded relationship it just talks about the relationship between two objects. It doesn't talk about the relationship of all the objects in the space. Because when we say one object is heavier than another, and we start putting that on a sequential weight line, or ranking them with numbers, that applies to everything. And so everything that's rated and ranked that way will be on that single thread, heavier than, lighter than. Whereas impacted by or affected by, things like that, those just operate between two objects. They don't operate between all of the objects. And so that global application of the relationship seems to be missing requirement that goes along with the logical group that's necessary to pick the proper algorithm. And so as I said, the important question to explore and address is what kinds of inferences, if any, are available to systems with multiple threads. And so, in looking at and emphasizing the fact that you do have local type of relationships that have zeros in the lower triangular and not all ones, can we actually find anything about the structure of our methods that will help us with inference and reproducibility of the analysis of systems that have multiple threads? And one of the things to notice and to think about now is that the lower triangular piece for a global is all ones. And the lower triangular piece for a local can have zeros in it. A local can also, have all ones in the bottom, but that's very rare. But you really don't know when you're going into doing a local type of relationship. But in both cases, both in the global and in the local, the upper triangular piece is filled with zeros. So what we'll find there is one of the things that we've been exploring and looking at is to say, okay, maybe we can use the fact that there's zeros in the upper triangular piece to help us do inference in a local, when we're dealing with a local relationship. And we have some ideas how we might be able to leverage that, maybe not a global inference, but maybe an inference across a group or a selected subgroup of objects. That's kind of a developing idea right now. So as we go through and start talking about the differences between local and global and inference and truth, you introduce the ideas that were developed by A.D. Hall in Metasystems Methodology, where he talks about three kinds of truth. We have formal truth, right, which is basically our inference. When we know in the global sense that we can do inference, so that's a formal truth. And we have factual truth. So factual truth is where we actually go out and measure, get information. So in the structural modeling process, we actually have both of these. What we do is we first go get some information about the real world situation, which, you know, spends resources to do that. We bring that information back, and then we use our formal methods to infer more information. So we have two sources of information, factual and formal. And what we're saying right now is these techniques that we're looking at, that the factual and formal seem to work very well under global relationships. They don't seem to work so well. The formal doesn't seem to work so well under local relationships. Now it could work, but there's a lot of uncertainty there. So that's kind of a balance. And then the other part, of course, is the value truth. And the truth of the value sentence is determined in a number of ways, including methods applied in formal and factual sentences. So when we really think about this, I think about the activity of structural modeling, we're usually trying to establish organizational values in a certain specific context under a certain specific set of conditions. So all three of these types of truth apply to the activity of structural modeling. And what we hope to do now is to start developing a little bit more of a discourse, a little bit more of a conversation about how these three types of truth can be addressed and used in sequence or concurrently to achieve certain goals. And now we have the little bit of expansion of the three types of truth. Again, this is A.D. Hall. And this kind of gives an example of these different types of formal, factual, and value truth. I think it's interesting to note that formal is really the only type of truth that's predicated. It says it's certain, but then of course it's certain in its methods, but there is some uncertainty with the factual basis that you're applying it to. So if you're applying it to real world objects and you're applying it to things that have been discovered from empirical experience, then it may be some uncertainty associated with that. But factual truth and value truth are uncertain. Okay, and so when we're talking about these three types of truth and certainty and uncertainty and risk management, then we have to really say, well, realistically, there's a little bit of uncertainty just in these methods and processes, the way that we're using them. And so what we want to do is minimize that uncertainty. So we go through and talk about uncertainty minimization. It's just then we can evaluate well, we can evaluate and discuss the output from a classical ISM software that's applied to a multi-threaded situation. So if you go into a situation and it's totally unknown, you don't know what the structure is, you don't know much about it, and you use that technique, use the ISM technique on a multi-threaded scenario, then you get an answer. And so is there some uncertainty associated with that answer? And I'm going to say yes. I think there's uncertainty associated with the way that the inference and the formal methods are being applied. They may not directly apply in that semantically in that case. But there's also uncertainty associated with the facts of actually gaining the information, people voting and talking about what's going on, and also some uncertainty associated with the value system. So it's not like that the application of this formal method in a certain case is the only source of uncertainty. You need to make a risk management decision of saying, well, is what the output from this process, is it better than what we have now? If what you have now is nothing, then you might say yes, it's probably better. And looking at the classical literature, there was like 4 grades of evaluation of the outcome of a session. And one of them was, well, we just, we're not really happy with this, we need to do it again. So, or, okay, ranging all the way up to, well, something has been done before, we're going to improve it. And so there's a number of ways to actually engage the structural modeling processes and try to reduce the uncertainty. So there's, that kind of gives a little bit of an idea of where I think the practice is right now, and that something is better than nothing. And what we're trying to do here basically now from a very basic standpoint is to reduce the risk and uncertainty associated with the application of the methods. And so that's kind of the area that we're going to focus on. Of course, these other areas will have impact, but there's been a lot of that done in the past. So last year I did a presentation to the local Seattle GNU Linux conference, and put out our little JavaScript application for addressing the 3 types of structural modeling. And of course, first type was strict order, 1 object per class. That's kind of the hierarchy, single-threaded. And then strict order, more than 1 object, 1 or more objects per class. So that's basically the hierarchy non-symmetric that has clusters in it. And so you take each cluster and condense it into 1 object. So that's again a strict order. And then clustering objects into classes. So each of the 3 approaches that are out there, and I've also put this up on GitLab. And so the basic idea of the single-threaded hierarchy is that you can use inference effectively. And with the non-symmetric single-threaded hierarchy is after you condense a cluster into a single class, then you can run a single thread through each one of those classes. So essentially, in both cases, what we're saying is these are global relationships, and that we are tracking that macro structure, the global relationships, even though some of the elements themselves might have multiple components that are a cluster of some kind. So we'll be, and then of course, the clustering piece where we cluster objects into classes, or we group things, that are similar. We'll be focusing on that specific definition of a cluster, plus a few others, and try to expand this and work it out to where maybe have a little larger semantic group. So, okay. So basically, now the software that we put out there, and that's out there right now, is basically an algorithm development support tool. So this software does not give you or tell you which specific element to get an answer on next. So the operator has to enter that. And and so you keep track of your algorithm, whatever your structural modeling algorithm that you're doing, you keep track of that kind of on the side as you're testing it and seeing the outcome here on the screen. And so this gives two text boxes for the entry of the row and column number of the next element to be selected. And then it gives an enter button. So basically what you do there is you, after you've put them in the text box, you enter it into the algorithm. And then it has swap entries and infer information. And so the swap entries basically is a tool that will take a object that has a green 1 in the upper triangular and will swap that so that that green 1 goes into the lower triangular. Because what we know is that all the 1s should be in the lower triangular and all the 0s should be in the upper triangular. And that is a piece of information, that's a macro piece of knowledge that we can use to incrementally structure the system. And then the infer information button basically is used on any configuration of the system, and you push that and it'll tell you if there's any inferred spots. And that will be, if there are, those inferred points will be marked with a 1 in the lower triangular, and the background a blue, it'll be a blue background. The strict order 1 or more objects per class essentially is essentially the same type of information, except it asks a initial question that asks, are the entries equal? And if they're equal, then what it will do is it will create a class of those two objects, take those two objects out of the main matrix, and create a list of those objects below the main matrix. In fact, it won't take both the objects out, it'll only take one. The leading one will represent the class in the matrix. But every time you have entries that are equal, the matrix will have to be reduced by 1. And then there's the cluster of equivalent objects, which is the classical clustering that's shown in the software of structural modeling and ISM. And the key difference between this matrix and the other two, of course, is that everything on the diagonal is green because things are equal to themselves. And so that's kind of a symmetric type of relationship, where the other ones were really asymmetric. And as these become clustered, and things are determined what class they fit into, then we'll just take this and the clusters listed below 1 per row. So again, below this particular matrix, then you'll list the clusters. And then the when they become identical, then again, the major matrix gets smaller and smaller. Okay, so that's essentially what we have right now. And that was written in pre-JavaScript ES6, which made some major architectural changes in the JavaScript language. So this existing software that's out there is going to be rewritten in a new modular format. And then that new modular format will allow us to establish reusable libraries, reusable math libraries, reusable logic libraries, reusable graphics libraries, so that it'll be easy to update, maintain, and expand and improve on these fundamental web applications. So that's kind of the fundamental piece of the software code that we need to look at, because that will change the architecture substantially as we go through. But that really doesn't help us in thinking about new algorithms. So can we come up with a new algorithm that we can apply to local relationships that give us some way of using the inference, the logical inference? And that's going to be a key aspect of the software as functionality as we go through and develop it again. We're going to be redevelop this new architecture, next new language features. And so we'll start thinking about this. And as I said, the existing software we have there right now is kind of like an algorithm development tool. So you should be able to test different ones, use different ones, and then we will create and distribute software, web applications that then are not an algorithm development tool, that actually will implement a specific algorithm that we've developed. So the first target piece of software to do that will be the clustering software, and we hope to get that done in the next couple months and get that rolling forward. And so we really want to see if we can reduce the risk and associated with the inference utilization, and also reduce the amount of resources, or optimize the amount of resources that are necessary to apply these types of activities. Okay. That's basically what I said. We're going to look at creating a new structural modeling algorithm to support the more difficult natural language structuring relationships. There's some aspects of the structured graphics and the mathematics that we'll check out. And what we would like to do is, document these reports and provide the software and do it in a level of detail that will allow other interested researchers to verify it if they want. That's our goal, is to put it out there so that it will be easy for other interested parties to either verify or deny, or invalidate what we've been doing. Okay, so specific software improvements, I talked about that. It's going to be ES6 and put into a modular design. And the modular design is going to be necessary to have an adaptive, algorithm and development and test environment. Also, this is really doesn't have much to do with the specific software applications themselves, but we're working on deploying this on a GitLab type of environment. And GitLab is a development platform, a CI/CD platform, but it's used mostly by the people that write software, and it's used mostly by the people that manage all the systems that the developers use. So I believe what we're going to do is we're going to actually use the GitLab code repository CI/CD for the development work, but we're going to use Google App Engine, I think, as the deployment target. So once we'll have a development on DigitalOcean CI/CD, then when we deploy, we're going to deploy to Google App Engine or Google Compute Engine. It'll give us a number of benefits. The first benefit is that we're going to be, once the algorithms are kind of stabilized a little bit and the code is put together, we're going to deploy these as Docker containers, and then we'll have the Docker containers. We can deploy those to Google, I think it's, yeah, Compute Engine, and into a Kubernetes type of environment, so that it's be a self-scaling type of software application, so that people need to, if you have a few people, you just have a few clusters or a few containers. But if you have a large group of people, then the architecture there and the self-scaling components of like the larger cloud pieces will allow you to scale that. Now that's not going to be really obvious when we're down here working with still in the logic and so forth, but it will become more obvious when we deploy a system where people can sign in. They have to sign in for an account, and then we automate all of the process where they answer questions and vote and all that with the data, distributed database backend. Then those more sophisticated types of web distribution systems will become more valuable then. So it might take us a while, but we're going to start now, start building the basic ideas and start working through it. So I guess, so the basic idea is that one general purpose structural algorithm is being challenged and reevaluated. And so the idea of, if you have one that you can use, in many cases that's good, but it depends upon, as I said earlier, if you have nothing and you use this algorithm in a way that it's not repeatable, is that valuable for you? Can you accept that kind of risk? Is it better to have nothing than what you have? And so that, I think, is that decision will need to be made on a case-by-case basis. I think what we've done by expanding and looking at this and saying, well, we have global type of relationships and we have local relationships. That's really a key discriminator to determine between different kinds of algorithms. And so this might be the first time that people have said, well, look, yeah, there's some areas where we could improve this, but we need to be able to specifically identify the area, right? This works good in XYZ area, but it doesn't work too well over in DEF. So you need to be able to determine that and then develop the algorithms, if you can, that allow you to improve situations where you're engaging with context in DEF. So that's kind of what that going there. Yeah, the other non-deterministic, non-repeatable system structure is acceptable as an answer. It may be to have that type of answer is better than nothing. right? But okay, the question we're saying here is, can we develop an algorithm that does better than that? All right. And so I really think a key area is starting to open up here, and that's an area where the non-computer, software folks can really have a contribution, and that's the idea of looking at these different natural language relationships that have a global attribute or have a local attribute, or are there others, right? How do we map a natural language relationship, its attributes, to essentially what we're saying is, how do we map that to a computer science algorithm? And there's this computer science algorithm. Does it make sense to do this in all cases, right? So I think that that's an important area. I know algorithms are becoming more important in general education, but I think in systems science and systems engineering, I think this is an area where you really need to do a lot more work. And I think it's an area where, as I said, people that are not, directly involved in writing the software and writing the code, producing it, can really have offered great benefits to this particular activity. So with that, I'm going to open it up for questions. Everyone went to sleep, was getting coffee.
There's one more graphic at the end.
One more graphic at the end. All right. We'll look at that.
No, not asleep. No, not asleep. Very interesting. Very interesting.
Okay, so one more graphic at the end. Okay, so we got the hierarchy, combined hierarchy, and network piece. Okay, we talked about that.
So,
yes, okay.
Joe, are you saying that one of these types is requires an algorithm that's non-reproducible, non-deterministic?
No, I'm not saying that at all. What I'm saying is from our experience, right? Our experience of taking the ISM software and applying it to a hierarchy that had multiple threads in it.
Yeah.
What the output from that was non-deterministic, because we would get different answers depending upon which ones we put in, what sequence.
Really?
Yeah.
What do you mean? Which sequence of pairwise questions you ask?
Yeah. So the multi-threaded examples, right, from the literature and what we published in our last reports. We just pulled out some of the graphics, right? Yeah. Pulled out some of the graphics that didn't have, how was it? It didn't have the step-by-step that said, this is how we produced this graphic, right? And so we said, okay, well, we should be able to use the ISM software, right, to reproduce this graphic, this level, these levels. So we went in and we said, okay, first we just tried to reproduce the one that we had, right? And I couldn't do that. I couldn't get it. I couldn't reproduce the levels and so forth using the ISM software from GMU. So then I tried multiple different ways, right? And I still couldn't do it. So that's what I'm saying. I'm saying that if I have a structure, I have a map of a situation, right? And somebody said, this is what we got using this approach, but I don't know their detailed steps of what they did. I just have the outcome.
Yeah.
So I look at that and I say, well, okay, I have the software, I got the outcome, I know, what the final structure is, so I can start asking questions, right? And I can start answering those questions because I know the final outcome. But I just couldn't reproduce it, that's all.
Really? I don't think that's type of thing's been published about ISM.
Yeah, I took it out of the let's see, the Science of Generic Design, I believe.
Yeah.
And also the handbook. Were just different examples of. I just went back through and I looked and I went through and I just did a quick scan. I said, well, what kind of relationships did these guys use, right?
Yeah.
And so the vast majority of the relationships that were reported, right, were global relationships. Only a small percentage of the ones that were reported were local relationships.
Reported in the literature about ISM, you mean?
Yeah, so the two books that I'm talking about as literature, this is now the Science of Generic Design.
Yeah.
And the handbook.
Yeah.
Those two, that's the literature I'm talking about.
Huh.
I just kind of went back through that.
So when you couldn't do it, you couldn't reproduce it in the GSU software. How about with did you also run it in your code?
Yeah, no, so exactly. That's an extremely good question. And so I started the analysis to say, okay, can I run it in my code, right? And that's when I stumbled across the fact, it finally dawned on me, right? That my code, the code that Mary and I have developed, basically needs to have a global relationship or an order to it. It has to have an order to it. And then I started thinking about the semantics of that. I thought, okay, well, yeah, I can see where these global relationships all appear to have order, some global order, right? But the local relationships don't have a global order, right? And so the approach that the algorithm that I tested on the global relationships depends on that global order. So then I started thinking, well, how can I change that so that I can use inference on a local relationship, right? And so I started working up that approach, and that's where we are now. So remember, the software that I developed doesn't impose any specific algorithm. It just implements the algorithm that the human operator is doing. So basically, it's an algorithm development piece of software. And so I'm in the process now of developing an algorithm, essentially, that will hopefully answer your question, right? But before we can get there, we have to address clusters. So we're going to do clusters first, and then we're going to do the next piece. That make sense?
I'm thinking.
All right. Well, there's no time limit. Take your time.
Since it's working, since the like the global and local are based on the same relational properties, why is it different? Why is the algorithm different?
Reachability. You see the reachability. See, this is when you're doing a reachability matrix, right?
Yeah.
I do this single-threaded one over here, that reachability.
Yeah.
Lower triangular is filled. Right?
Yeah.
This guy here at the top can reach everything at the bottom, right? This next guy down, it can reach everything. Everybody can reach everybody, right? But in the multi-threaded, the guy at the top can reach everybody, but the second guy down, he can't reach that other guy over there. And at the third level, you know, the guys on the left side can't reach the guys on the right side, right?
Yeah.
So the reachability, so there's zeros in there.
But if you start with an adjacency matrix and iteratively multiply the matrices, you end up with a reachability matrix, whether it's single-threaded or multi-threaded. Don't you?
Well, okay, but now I believe that that's a correct statement because that's the mathematics, right? But the point I'm trying to make is that reachability, so the semantics, what is the semantics of reachability, right? The natural language semantics of reachability. And then the mathematical implementation of reachability, right? Are these being properly aligned? Are they in correspondence, right? That's the sim area, right? So we're taking the basic mathematics function, right? And the real world natural language, and we're evaluating them. That's really a good question. That's what we're trying to address. The difference is the reachability. In my mind, one of the differences, let's put it that way, one of the differences is the reachability.
I think the issue there is whether you have a transitive relation. And so the question is, do you define that in advance, that you do have a transitive relation, or you have a transitive version of the, you know, a transitive relation that is what a transitive embedding, the transitive relation that captures the essence of the relation you start with.
Yeah, so they're both of these are transitive. They're irreflexive, asymmetric, and transitive, both of them.
So in those cases, now so you start by mandating that you have a transitive relation.
Exactly. That's the first thing you do is you pick the structuring relationship. That's what you can pick.
Right.
You can pick that, right?
So I'm thinking about the other language related to this global local question. And isn't this the question of a total ordering versus not? Just looking that up. A linear order, total order, simple order.
Yeah, there's a lot of them.
Yeah, so those are related to the global. Those are all, and total order, I guess, is the general case, or the one that is preferred name. So there's a total order, and in your multi-thread, there's a partial order. Now it's interesting that.
Okay, I'm not sure that I see.
If you look at Wolfram, they say that there's a the comparability question. It's interesting because strict versus non-strict, total versus partial, have ambiguities when we think about the meaning of them. The cohort elements on a level there they're not
they're not connected.
Right, they're not connected. They're not comparable. Right.
They're not connected.
Right.
From a mathematical standpoint, so they can't be in order.
Right, exactly. That's what makes it a non-total order.
Okay, well,
Yeah, so
it's not an order.
there's no order relation between those two elements.
Or the ones at the bottom, or the ones at the bottom.
That's
either.
right. So
Or the ones at the top.
levels, right?
Yes. I think you're perfect.
Yeah. So there's no ordering across levels. Now, sometimes there's an assumption of that there's some kind of equivalence class that holds on a level.
Yeah,
I'm thinking just in hierarchy theory, sometimes there's an assumption that, that these are organs, cells, that kind of thing. So there's some equivalence class that does hold for a level, but that's not necessarily the case. So
right.
you wouldn't want to impose that.
Right.
Yeah.
So the question, and I think it's really, it's you've expressed it really well. And the question is this: is that can you use inference when you don't have an order? Because an order basically gives you a lot of information. But if you don't have an order of any kind, can you use inference? And so I'm thinking about it on a couple different levels of the way that this information is presented. And I think there might be some areas where the semantics would allow that to happen, because remember, this is a matching of the mathematics to the natural language real life scenario, right? And neither the mathematics relation semantic is not controlling, and the real world relationship semantics are not controlling. Really, what's controlling is the structural integration modeling semantics, where the practitioners there, know how these things work, and there's going to be some risk assessment involved in that. But yeah, so I agree with you 100%, Janet, and that's kind of where we're going with the next set of exploring the algorithm.
I am pondering the same question that Kevin's pondering of, well, I guess from another point of view, how much does the software allow you to discover the relationships, and how much do you need to know in advance?
Great questions. Yeah. So what the software does basically is it gives you a visual picture of the math, right? And it gives you some color codes of what the state is right now, and then allows you to implement any algorithm that you're testing that you sketched out by hand, right? And you're inputting it. And so it really is designed to help you visualize the structure of your algorithm. And then think about that, right? And then map that back to the standard computer science approaches, and then also be able to think about what those semantics mean in real life. So, yeah. Hopefully that answered some questions. How you doing, Kevin? Got about another 3-4 minutes?
I'm still curious why multiplying the matrices until they converge is different for single thread versus multi-thread.
Okay, let's see if I can do an example of that with semantics.
Yeah, I think that'd be worth going through in detail.
Sure.
And also, I think the reproducibility issue is a publishable thing. But
okay.
We need to look at more algorithms, and there's still there's software out there in England and Canada and Mexico, and I don't know if they're still retrievable from other companies. Even IBM had it, Northern Telecom, NASA. I mean, there's still algorithm, people have different versions of the algorithms out there. And for something like reproducibility, it'd be worthwhile seeking them out and, trying to run it through a battery of things. Like,
would you like to work on that?
Yeah, it's something that would complement the test bed. The test bed is to look at a bunch of examples on one or more software packages, but what I'm just talking about now is to try to see where those packages are. There's like 20. It went to at least 20 places already by the early 1980s.
Yeah.
And it'd be kind of an archaeology to find them, but.
All right, well, that's good. So is there any final comments people would like to add before we sign off for December?
No, thank you, Joe.
You're welcome. Take care. We'll keep in touch. Who's going to do, what is it, December, will be 16th?
We're going to be on the road at that point,
Okay.
so maybe we'll skip this month.
Pete, I was going to suggest that we do an example that Peter presented me with.
Okay.
And maybe do run your code in parallel with the Cognoscope and see how each of them might address the same one, or just pick one and do an actual example online.
Why don't we do that for the 16th, Kevin? Okay. I'll put that out, and if you want to send out a little bit of information,
Yeah, I'll put something together.
Cool.
Yeah, we'll try to call in from the side of the road.
Thank you, Janet.
Okay.
Right.
Yeah, sounds interesting. Yeah.
Okay. Take care.
Bye-bye.
Okay, bye-bye.
I know.
All right.
Bye, Mary.